Page IN16, we're going to continue our lesson on independent events. So looking at example 4, Shannon will roll 2 number cubes numbered 1 to 6. What is the probability the sum of the numbers is either even or equal to 11? So either even or equal to 11. We probably need to make a table or list out all of our different possible outcomes. And I don't know if we've mentioned this or not. Listing out the possible outcomes is called a sample space, if you ever hear of that. So what they did is they listed the different sums. So like if you rolled a 1 and a 1, 1 plus 1 is 2. That's how they got the numbers there. 1 plus 2 is 3, and so on. So we're trying to get either an even number or an 11. So if you look what they did, they listed out all the possible sums, and then they've highlighted kind of in pink all the even sums, and then they highlighted in yellow the sums that would equal 11. And then they added up all the pink boxes, which was 18. It was half of them. Makes sense. Half are even, half are odd. So that's an 18 out of 36 chance. The book reduced that. I mean, technically it can reduce down to a half. What I would probably do is just leave it for right now as 18 out of 36. Sum of 11, we've got a 2 out of 36 chance. The reason I wouldn't reduce yet is because we want either an even or an 11. Even or an 11, how we find those probabilities, because they are mutually exclusive, we'll talk about in a minute. If they're mutually exclusive, we're going to add those together. So we're going to add 1836 plus 236 is 2036. And then we can reduce that down to 5/9. So my reasoning for not reducing is I've got to have a common denominator if I'm adding these together. If I reduce, let's say I reduce the 1836 down to a half, that's a half, and then my other one reduces to 1/18. Now I've got to go and get a common denominator again. I already had one. It was 36. So there's no reason to reduce and then have to go back and get a common denominator. You already have it, just use it and then reduce afterwards. So what do we mean with mutually exclusive? Mutually exclusive means that there's no overlap between the favorable outcomes. In other words, in this case, we're trying to get either an even number, a sum that's even, or a sum that's 11. 11 is not even, so there's no overlap. It's not 11 and even at the same time. Example 5, we're going to talk about some things that are not mutually exclusive. So here we've got Quincy rolling 2 number cubes, 1 through 6. What's the probability the sum of the numbers is rolled is either even or greater than 10? So we don't care. It can be even, it can be greater than 10. Either of those is what we want. So again, they've got their table here with all the sums. Evens, they kind of highlighted in pink. Greater than 10, they were kind of highlighting in a yellow, except for if you'll notice this corner is a different shade. The reason that's a different shade is it fits in both groups. It's even and it's greater than 10. Okay, so basically you just got to make sure you don't count that same one twice. So if it's not mutually exclusive means there is an overlap. There is an overlap between favorable outcomes. And like I said, you just got to remember then, make sure you don't count something twice. So what the book did is they said, okay, we've got 18 out of 36 that are even. We've got 3 out of 36 that are greater than 10, because we had an 11, 11, and a 12. But then they're saying we had one number that was even and greater than 10, so we'll take that out because right now it's being counted twice. And then they said that's a 20 out of 36 chance. Probably simpler for you guys would be, if you're going to do this table anyway, I would just look at, I did evens are all these, and then so these are all evens, and then I'm looking for sums greater than 10, so 11, 11. The 12's already circled. Then you can just count how many you've got. If you just count how many you've got there, there's going to be 20 out of 36. And then you don't have to worry about, I'm going to add these two fractions and then I'm going to subtract this other fraction. Just count how many things you've got there and you'll be good. So if we look at the try it, Jamie will roll 2 number cubes numbered 1 to 6. Are these events mutually exclusive? So they're not asking us to find the probabilities, they're just asking us if they're mutually exclusive. In other words, is there not an overlap between them, or if not, then they're not mutually exclusive. So part A, rolling sums of 6 and multiples of 3. So just to make sure we understand what they're meaning by that, sums of 6 would be numbers that add up to 6. So we could have going back to our tables that we had earlier. So here's our table we had earlier. Sums of 6. And the interesting thing about this is sums of 6, they'll all be in a row here, or kind of in a diagonal. So if you had 5 and 1, 4 and 2, 3 and 3, 2 and 4, 1 and 5, all those are multiples of 6. And then the other thing is multiples of 3. So multiples of 3 we would have with the 3 and 3, those are multiples of 3. And so that's going to be not mutually exclusive. Okay, not mutually exclusive because the 3, 3, those are both multiples of 3. Part B, it talks about odd sums and multiples of 2. So odds, pretty much it's going to be all these white ones are the odds plus those sums of 11 down here. Those are all the odd sums. And then multiples of 2. Multiples of 2, 2, 4, 6, 8, 10, so on. Those are multiples of 2. So those are not the same as our odd ones, so those are mutually exclusive. And I guess real quick then, going back to that last one we just talked about, sums of 6, multiples of 3. I maybe wasn't thinking correctly about what they were asking, but multiples of 3, if it's a sum of 6, 6 is a multiple of 3. So those are all identical, basically. All of the sums of 6 are also multiples of 3. So for sure, that was not mutually exclusive. So if you look at the key concept, just kind of recapping things. First of all, they're independent. We have independent events if the outcome of one event does not affect the outcome of the other one. And then to determine the probability of 2 independent events, we can multiply the probabilities. So really we've got in this section kind of two different things. Some cases we talked about multiplying probabilities, some cases we talked about maybe adding. So just be careful with what operation you do. So on the do you understand number 2, how can you use the probability of the desired outcome to find the complement of an event? So to do that, we can subtract the probability of the desired outcome from 1 to find its complement. So for example, if we worked something out and its probability is 1/8, the complement of that you could think about would be 1 minus 1/8, which would be 7/8. Or just think about what two fractions could I add up together to get 1 would be another way of looking at that. So look at the do you know how number 4. One of 3 contestants will be randomly selected to win a prize. One of 3 different prizes will randomly be awarded to the contestant whose name is selected to win. The tree diagram shows all possible outcomes of this contest. So the question is, what is the probability that Whitney will win prize 2? So kind of we have two different things happening here. First of all is Whitney winning, and then second of all is her winning prize 2. So the tree diagram's already drawn out. We can look at it from that perspective. We'll also talk about how we could do this just working with the probabilities and not having drawn anything out if you want to. So if we look at the tree diagram, you can see there's 3 options with Pedro winning, 3 options with Whitney winning, 3 options with Brian winning. So we've got a total here of 9 different routes. Only one of those routes has Whitney winning prize 2. So from the tree diagram, we can look at that and say that Whitney has a 1/9 chance of winning prize 2. Also, we could look at this. The numbers aren't bad. It doesn't take long just to draw a tree diagram or to write a table out of the possibilities. If we didn't do that, another option would be looking at the probabilities of each one of these. So first of all, looking at the people, there's 3 people here, so the probability of Whitney winning, she's 1 out of the 3 people. So probability of Whitney winning a prize would be 1 out of 3. And then we can look at what the chances of her winning prize 2 would be. So once Whitney wins, she's going to get one of these 3 prizes. So she has a 1 out of 3 chance of getting any of them. So she has a 1 out of 3 chance of getting prize 2. And then if you just multiply those together, that would be another way you could get that to be a 1/9 chance. Okay? And again, if it's easier for you to look at the tree diagram or to look at the table, then just do it that way. Okay, as long as the numbers aren't really big, as long as there's not like, 500 prizes or something, probably wouldn't want to do that on a tree diagram, but otherwise, not too bad of a deal working it out that way. Number 5, table shows all the possible outcomes for flipping a coin and spinning the pointer of a spinner with 4 equal sized sections labeled 1 through 4. What is the probability that the pointer will not stop on a 3 and the coin will not land on heads? So this is kind of an opposite question. We want it to not be a 3 and not be heads. So one of the options on our table that's not a 3 and not heads would be tails 1. Another option would be tails 2. Another one would be tails 4. And that's it. So that's 3 out of, there's a total of 8 different possibilities here on our table. So we have a 3/8 chance. The other option you have if you want, again, it wouldn't be bad at all just to do the table. To not get a 3, not a 3, we could get a 1, a 2, or a 4. That's a 3 out of 4 chance. And to not get heads, not get heads would be getting tails, which is a 1/2 chance. And if you multiply those, you could get 3/8 that way also. Okay, again, this may be just the way to go. Maybe an easier way for you guys just to draw the table and look at it instead of trying to figure that other way out. Part B, what's the probability either the coin, either means it can be one or the other, either the coin will land on heads or the spinner will land on a 3. So one option that fits that would be heads 1 because it's got the heads. Another option, tails 3 because it's got the spinner landing on a 3. Heads 3 would be another one. That actually is kind of double covered because it's got the heads and the spinner on a 3. Heads 2 would be another one because it's got the heads. And heads 4 would be another one because of the heads. So if you look at that, we've got a total of 5 out of 8 different possibilities. So 5/8 chance. This is one that's an example of not mutually exclusive. If you remember one of those we mentioned, the heads 3, that would have been kind of covered in both sections. So if you would have tried to work it out by hand, you could have said, you know, chances of getting a 3 would have been 2 out of 8 options. 2 out of 8 options in the table has a 3 in it. 4 out of 8 options has heads, but then we'd subtract the 1/8 because the 1's covered twice. Okay, and like I said, probably the best way, the easier way for you guys is just going to be to draw that table and work it out from there. It's a little bit less thinking involved with what's going on. So this gives you an idea of how to work with probability of independent events.